My name is Eneko Aguirre. I am the director of IT, the Basque Center for Language Technology, and it's my pleasure to introduce the 2021-22 webinar series, where we have a great lineup of speakers, starting with Hinrich Schuetze, which I will introduce in a moment, but also every month, every beginning of a month, we have researchers talking, who will be talking about the last advancements in natural language processing. You can see the list here, and you can also check the recordings of the webinars that we had last year, as well as registering for the next seminars. So I'll introduce very quickly Hinrich Schuetze. I don't think he needs much introduction. He's a very influential person in the field. He has been in universities and companies alike, and he's been very influential, especially for his two books in information retrieval and natural language processing, but also because every time he has devoted time to a research topic, that research topic shined. For instance, coming to the topic that he will be speaking today, after pre-trained language models made such big advancements in natural language processing, technical prompting or context in context learning started to show spectacular results, and in part this is thanks to him and his research, and he will talk about this in a minute. Okay, so I'll make you presenter, Hinrich. 1 second.
Yes.
Oops, somehow. So I think you can share the screen now.
And I will share my screen, right? Or just an application?
There is a button to share the screen.
Okay.
Below.
Can you see my screen now?
Yes, we can see the small slide, not the full screen slide.
Yeah, this is unfortunately a disadvantage of the presentation software I'm using, that it's not possible to go full screen.
That's fine.
How big is it on your screen? It should be about, I mean, the height should be about, I would say, 80% or 85%. Is that what you see?
Yes, yes, yes. In my case, I can see it correctly.
Okay, great. So then I can start?
Yes, please. So it's the floor is yours.
Okay. Yeah, thank you very much for your kind introduction, and thanks a lot for inviting me. It's very nice to have an opportunity to present our work here. And I'm actually going to present a version of an updated version of our NACL talk, a NACL invited talk. So I apologize to those of you who already know the talk, although the last about third or quarter is going to be new material. Okay, so I want to start with a question: how do humans learn? And a pomegranate. Let's look at a typical example of human learning, how to open and eat a pomegranate. And I want to show you or maybe you guys are going to do that, a YouTube video. Please read the closed captions. I'm not sure whether the audio is going to work, so reading the closed captions is best. And pay attention to two things. One, the description. So you're going to see an instructor who is going to tell you how to open a pomegranate. So pay attention to the instructions and to the number of training instances you see in that video. Okay. So I believe that you are going to show that on your side, the video now, or should I show it?
Yes. I don't know which will be the easiest way. Maybe you can try to show it, and otherwise.
Okay, then I will try to show it. Okay, 1 second. for some reason it's not showing.
We can see the screen. We can see the window.
Oh, there,
It's coming slowly.
there it is. Yeah. So I think there's going to be 6 seconds of
Yeah, commercials. Yeah, usual thing.
Pomegranates are my 4-year-old son's favorite. We eat these things. We needed to find an easy way to get at them. Because let's face it, these things can be kind of a pain in the butt to open, and they can be messy. But here's a way that is much easier.
So pay attention to the descriptions that the instructor gives and to the number of training instances you see in this very short clip. We're just going to watch the first 45 seconds.
Now what you're going to need is obviously a pomegranate, along with a knife and a bowl of cool water. Now, pomegranate is a simple fruit. If you look closely at a pomegranate, you will see on the outside that there are 6 ridges. And what you want to do is take your knife and just score the pomegranate along the ridge. What that means is you don't want to cut through to the seeds in there. You just want to cut through the skin. 6 cuts. Now what you want to do is break your pomegranate open above your...
Okay. Can you see my slides again?
Yeah.
Yeah.
We
Okay,
can see this.
great. Okay, so what did we see here in the video? The teacher gives a detailed description of the task and the solution. The task description is we are looking for a way of opening and eating a pomegranate that is not a pain in the butt and that is not messy. There's a solution description. Part of it is to score the pomegranate along the ridges. Of course, the YouTube video goes on and there's more details how you open the pomegranate, but that's part of it. And then there are very few training instances of scoring the pomegranate along the ridges. So if you counted, there were 3. There were 3 ridges that the instructor actually scored in the video. So I would argue that this is a typical form of human learning. We have a detailed description. We have an instructor or some other source that gives us a detailed description. And we have very few training instances. In this case, just 3 training instances. Now, of course, human learning is very varied. And I'm sure there are cases where we learn without descriptions, for example, just by imitation. And there's probably also cases where we have lots and lots of training instances. And I mean, yeah, so certainly it's not always the case, but it seems like this is a fairly typical way humans learn. We have an instructor available, they give us instructions, and we don't have that many training instances. So compare that with our typical machine learning setup. No descriptions, large training sets, and even in few-shot learning, in so-called few-shot learning, often there are actually thousands of examples. So that's not really few-shot, you could argue. So the motivation for our approach is humans take advantage of task descriptions. Machine learning models mostly don't. I mean, there's an increasing number of exceptions, but especially 2 years ago, this was basically non-existent. And how can we incorporate task description into NLP? How can we change this situation? So that's already the motivation part. How do humans learn, and what we want to do in machine learning, similar to humans. Now I'm going to introduce our particular way of making use of task description, which is pattern exploiting training, PET. Then there are going to be some experiments comparing PET and GPT-3. Then we're going to apply the same basic ideas to debiasing. And if there's time, then we have some related work at the end. Let me introduce the team to you. It consists of Timo Schick. He came up with the idea and did the actual work. Then there's Sahana. Sahana is a professor of media anthropology here at LMU Munich. And she collaborated on the debiasing part. And she's particularly concerned about making sure that the communities that are affected by hate speech or extreme speech, that these communities have a say in determining what's happening online, as opposed to just leaving it to companies and governments. Okay, so now I want to introduce our method for using task description, pattern exploiting training, PET. So, and I'm going to explain it for a particular example, the task of sentiment analysis. So we have our task here, it's sentiment analysis. So we have a restaurant review, excellent pizza. We have some labels, 0 and 1 here. And then we train a classifier which takes a restaurant review as input and returns one of the labels. So that's our task, and we want to convert this task to a task description. So that's a description of the task in natural language. And we want to do that because we want to use a masked language model for solving the task. And a masked language model understands natural language. And I'm going to be a little bit sloppy with the way I talk about it. I'm just going to say the masked language model understands natural language. Of course, it doesn't. The level of natural language understanding compared to a human is very I wouldn't say negligible, but I mean, we still have a long way to go to get to human performance. But I think we have made a huge amount of progress in the last years, and these masked language models, or language models in general, actually do have some basic language understanding now. I would think most people would agree with that claim. So by creating this task description, we want to make use of the language understanding capability of these models. The idea is that if you explain the task to the language model, then it will be much easier for it to learn the task, to do it well. And it will only need a few training instances to do it well. So that is the basic idea of what we're doing here. Okay, so how do we actually create the task description? So first, we map the labels to natural language words. So we map 0 to the word bad and 1 to the word good. Since the masked language model understands the meaning of these words, bad and good, it now has an understanding of what the labels of the task are. So that's the first part of the task description. The second part of the task description is the pattern. And here we basically, let me just show you the pattern first. One of the patterns is input, it was mask, where we put the restaurant review here for input. And then the masked language model will put for this mask one of our two verbalizer words, either bad or good. So then you have the review here and it was mask there. That's what's filled in by the masked language model. Now there are two criteria for choosing this type of pattern. In our approach, the patterns are designed by a human. So we rely here on the designer's understanding of the task, of the system operators or the machine learning engineers' understanding of the task. And that is the first criterion for finding a good pattern. It must correspond, of course, to the task. And I think everybody can agree that that is the case here. If you have in natural language a restaurant review here, and then it is followed by the sentence, it was masked, then this adjective here will most likely contain an evaluation of the restaurant, a summary, and that can be used as a label in our context. So that's the first criterion for choosing a pattern. The second criterion is that it should be something that the language model understands. And so it must be something that is a good match for the distribution that the language model was trained on. And again, we didn't actually check this empirically, but this type of context, input, it was mask, maybe not literally, but that pattern of words and of language occurs a lot in corpora. And since the masked language model is trained on lots and lots of corpora, it will have encountered this type of language many times, and therefore it is comfortable with it and can work with it. So that's the task description. It consists of the pattern and the verbalizer. And the idea, again, is since the language model understands language, we give it a description in natural language of the task, and then it has a head start in learning the task well. Okay, so that's one part of what you do. And the second part is supervised learning or fine-tuning. And that's really simple and kind of straightforward, but it's a critical component which distinguishes this work, especially from GPT-3, as I will point out later in the talk again. So how does the supervised learning part work? So we have a training instance. Here we have a restaurant review, excellent pizza, and the label 1. We can use our pattern, review it was mask, so we substitute the review for the review variable here. Then we get a filled-in pattern that is excellent pizza, it was mask. We input that to the MLM, and now the MLM is going to find the best match for mask in this context, and we restrict that to the two verbalizer words, so to good and bad. So of course it will make predictions for all words, but we are only interested in good and bad. So the question is, how well a fit is the word good here, and how good a fit is the word bad here. So then we get a distribution over our verbalizer words, and that gives us already a prediction for the task. And now we can fine-tune that simply by using cross-entropy and just using this as a training instance. So what happens now is that the is tuned for this particular pattern and for our task sentiment analysis. Now, I said earlier that the language models have a basic understanding of language, so they can actually solve the task without any training. And we will see that that is the case. But of course, the performance is not very good because you can always get better performance by fine-tuning. And we will see that the fine-tuning is, of course, very important for getting good performance. So the result of this is that we have now a fine-tuned language model that is fine-tuned for the task and for the pattern. Okay, and so we could do this for a single pattern, but it is actually important to do it for multiple patterns. And I will explain on the next slide why multiple patterns are really important. This is not difficult or complicated, but since it's so critical, I'm going to go through the steps here so that you see how we do this. So let's say we want to classify this unlabeled instance X. So now we're going to use multiple patterns, P1, P2, P3. We have a fine-tuned language model for each of them, MLM 1 through 3. And each of them is going to give us a score for this unlabeled instance. We can aggregate that simply by summing the logs, for example, and then we can train a final classifier, which will give us the decision on, for example, sentiment analysis. So it's very easy to use an assembling approach here. And just to give you an example for that, again, for sentiment analysis, so here we have 5 labels now, the Yelp task, 1 star through 5 star. These are our verbalizer words, terrible, bad, okay, good, and great. And these are the patterns that we use. It was mask, review, just mask, review, review, all in all it was mask, review, in summary, the restaurant is mask. So what I want to point out here is that these two patterns are quite different from these two patterns. And that kind of draws attention to the fact that the limit here is the limit of the imagination of the system designer. So you can design lots of patterns, and the hope is that you will find one or a few that work well. But of course, it's difficult in a few-shot setting. It is difficult to determine which ones are the good patterns and which ones are the bad patterns. So we protect against relying on a single pattern, which may be a bad pattern, by using lots of patterns. So why are multiple patterns critical? The patterns provide human expertise. The more, the better. I would say that realistic few-shot learning is difficult without human expertise. If you have true few-shot learning, very few training examples, if you want to solve the task well, then the information has to come from somewhere. And I think human expertise is a very good source for additional information in addition to the few shots. And it's also very realistic, because if you are in a few-shot learning situation, then there is a machine learning engineer who is trying to get the system to run, and their expertise is valuable. Now, can we try out multiple patterns and just keep the best one? So maybe you want to write down a bunch of patterns and you just keep the best one. So our opinion on this is no, because we don't have a deficit in true few-shot learning. If you had a large deficit that would tell you reliably which pattern is the best pattern, then you wouldn't be in a few-shot setting. Okay, so that's why multiple patterns are really important, and I'm going to return, if I have time, to that point at the end of the talk. Okay, and there's one last element, again, to make it work really well. It actually just gives us a few percentage points, but that's, of course, important for getting good performance, I mean, for doing well on the benchmarks. And so that's iterative training. And what we're using here is a very well-known idea from bootstrapping and semi-supervised learning. We're reusing that here, and it seems to be pretty effective in this case. So what we do is we need a set of unlabeled data. And so we start, and we're going to train several generations of models. So this here is the first generation of models. They are trained the way I just described, so just on the few shots. And what we do then is that we run these models on all the unlabeled data. And then the models will classify the data. So now we have artificially labeled data. We keep of those artificially labeled data only those that have the highest, for example, 2% or 5%. And that gives us then new training sets that are enlarged. They contain the few shots, but they also contain these high confidence automatically classified training instances. So on this, on these enlarged training sets, we can now train the second generation of models, and we keep doing that until we train our models on the entire training set, automatically labeled training set. And then at the end, there is a distillation step where we label the entire data set with these final models, and then we just fine-tune a language model like Roberta on this now very large training set. Okay, so that's PET, IPET, iterative PET, and I will use this abbreviation IPET to refer to iterative PET. Okay, so those are basically the elements of our pattern exploiting training. So we leverage the MLM's language understanding. We use multiple patterns because this is designed for few-shot learning. It is useful in few-shot learning. It is true few-shot learning. We don't need a development set to use this in reality. And we use supervised learning. In contrast to other work, especially GPT-3, we use supervised learning here, and we fine-tune our language model. Before I go on to the experimental part, I want to ask the question, what exactly is a task description? So here we have a task description from GPT-3. So we have the task description proper, that is translate English to French. Then we have 3 training instances. Thanks, merci, hello, bonjour, mint, mont. And then we have a closed question, cheese, and then the language model puts its answer here after arrow and cheese. So that seems perhaps like a straightforward task description, but it's actually not straightforward. Why? Because there are many ways to word this task description. So in GPT-3, they chose translate English to French, but you can think of a dozen other ways to formulate the same idea. You could ask, what is the French translation of this? Or you could use the arrow and say English arrow French instead of using natural language. So you can easily come up with lots of different ways of wording this task description. And the same is true for the training instances. Here they chose this arrow, which actually is not natural language, right? But it is something that presumably occurs a lot in the training set, in the pre-training set, and therefore it's a good way to use that. And it's a very succinct way of posing the problem as opposed to using a lot of words, which may also help. So again, there's a dozen ways of doing it, and they chose one particular way. And we don't know how they exactly did that, but presumably this is a way that works well. And that's why that's what ended up in the paper. And so our experience is that it's actually very sensitive, and I'm going to show you some experiments on that in a moment. It's very sensitive to the particular way you formulate or word these task descriptions. And so it's actually not a straightforward task to come up with task descriptions. Let me just run through 3 task descriptions so you can see a little bit of the complexity of the task descriptions. So this is the one we already saw, and the only thing I want to point out here is that, of course, you need a close coordination of the verbalizer with these mask positions in the pattern, because we are substituting the words for the mask position. So they need to be coordinated, so you need to design them together, of course. Here's a second example. It's for the word in context task in Superglue. I can best explain that by reading to you our pattern. So that is, does W have the same meaning in both sentences? Mask. So what's given here is 2 sentences. They both contain an ambiguous word, and you're supposed to answer the question, does this ambiguous word W have the same meaning in both sentences? And the answers are yes or no. So in this case, the verbalizer maps the label same sense to yes and the label different senses to no. So what's interesting here is that in contrast to the previous pattern and verbalizer, here the verbalizer is very simple. It basically just embodies a simple binary decision. So all the work here, all the workload here is on the pattern, and the verbalizer contributes relatively little if you compare it to the previous pattern verbalizer pair. And the last example I want to give, because it's also quite different, is the Winograd Schema challenge. Here, again, I'm going to read to the pattern to explain what the task is. In the previous sentence, the pronoun star p star refers to mask. So the task is that you're given a sentence, there's a pronoun that is marked by stars. So for example, star, he, star. And then what you're supposed to put here is the noun or name that it referred to, that the pronoun referred to. So it's a reference resolution task. And in this case, our verbalizer is simply the identity. So we take all eligible antecedents in the sentence, and that is the universe for this verbalizer, and each of these antecedents is just mapped to itself. So you can see that, again, this is quite different from the other 2 examples. So there's a lot of creativity involved in creating good verbalizer pattern pairs for a particular task. So what exactly is a task description? It's not a simple description of the task. It's actually not really a good name for what we're doing, task description, but I'm using it because we haven't come up with a better way of calling it. what it really is it's a complex translation of the structure of the task into plain text. Why plain text? Because that's the only thing that the pre-trained language models understand, because they're pre-trained on plain text. So that's their medium of communication. So we have to translate the task into the medium of communication of these language models, and that's plain text. And the examples I showed to you demonstrate that it's not really a cookie cutter method that you can apply. You really have to use your creativity and be imaginative to come up with good task descriptions. Okay, let's move on to some experiments. First, only on PET. So what you see here is, and here in the lower right corner, I'm always going to indicate the language model that we're using, because remember that what PET really is a fine-tuned language model. So we always building on top of a language model. So in this case, the language model is Roberta Large. So here we see results for Yelp Full. For 10, a training set of size 10. Yelp Full has 5 labels. I showed you the 5 labels before. So it's a sentiment analysis task. And so we are giving 2 training instances for each label. Right. And so here you see the performance of the simple supervised performance. That's Roberta Large. And you can see that that is barely above baseline. It is basically baseline performance, which is not surprising if you just have 10 training instances. Here you see the supervised PET performance. So that's 33.8. And that's already an indication that we are onto something interesting here, because by the way, I didn't explain unsupervised PET to you, but maybe you can imagine how it works. It just uses the task description and no labeled data. So just by using the task description, we get an improvement of 12%. So that's a demonstration of the power of the task description. Then moving on to supervised learning, which I explained to you in detail. First, let's look at individual patterns, and you see that there's actually a lot of variety between the patterns. And that's why it's so crucial not to be dependent on a single pattern. This here is the worst pattern of the 4 I showed you, and this is the best pattern. So you have more than 10% performance difference. Here are the patterns again, the 4 patterns. And I think it's very difficult to guess, if not impossible, which of these 4 patterns here has a performance of 40% and which one a performance of more than 50%. And so again, that's why it's important for us to have an ensembling approach that doesn't need to select patterns. Okay, and if you use regular PET, then you get 52.9% performance here, and if you use iPad, then you get 57.6%. And I think that's a very good result for 10 training instances, 57.6. I don't think there's any other result that good for just 10 training instances. So I think that's promising. Here's the effect of training set size from 10 to 50 to 100 to 1000 training examples. By the way, can I ask when I should stop? I guess around 4 or when?
Yeah, I think we started late, so 4 will be fine. Yes, and then also there are already some questions. I guess you prefer to take questions after the talk.
No, you can ask them now. You can ask them now.
Okay.
I mean, not too many, but maybe we can do a couple now, and then yeah.
So I think I can read from the chat. So Matt Maule, she's asking whether the patterns appear to have very similar semantics. Would you say to some extent that is trying to exploit the properties of the training set? That is, for instance, the Max language model saw many more reviews with overall it was X than in summary it was X, despite the identical semantics.
I'm not sure I got that. So I understood that it looks like the semantics, the true natural language semantics of the pattern seems to be similar, right? Is that part of the
Yeah,
question?
so I think well, maybe Matt can take the mic. Make the question.
Yeah. So sorry for the confusion. I was mostly interested in why it does better for some of the patterns than others if they're practically identical in terms of semantics, and if that's possibly just the language model understands that prefix more. Like it's seen more data that uses that specific phrasing.
It has seen more data of that phrasing, or one of the patterns is easier to learn for the language model than another, even if the amount of data is the same. Because, I mean, as I said in the beginning, I'm sloppily saying that the language model understands language, but it doesn't. Its understanding often is very limited, and it's very easy to confuse language models, as has been shown by many people. So if the language model does something that doesn't conform with expected human performance, then I think there are many reasons for that, and I don't think it's surprising.
Okay, thank you.
So maybe another question.
Sure.
So I think I can read this one correctly. Antonio Rueda asks whether it would be possible to generate patterns, I guess automatically, for instance, using cosine distance based on the similarity of sentences.
Yes, that is possible, and there's lots of people who are working on this or have worked on this, and I think that's certainly very interesting to do that. And so my personal inclination is to say I think it's good if we impose inductive bias by designing the patterns ourselves. We want to bring to bear our human expertise in machine learning. We don't. I don't think it should be our ideal to do everything automatically. And if you have other sources of, if you have click data or other interaction data in social media that you can use as additional signal, then it may be something, a different story. But I think we need some good signal. If we only have 10 or 50 training examples, we need some additional signal. And I think human expertise is a good signal. There are, of course, other signals that may be available, but in some situations, I think human expertise is the best signal. So I don't think it's a bad thing if we have to hand design them.
Mm-hmm. Okay, thanks. I think we should go on.
Okay, let's go on. Let me actually skip these two slides.
So just to be clear, we can do until 4 more or less, and then take like 15 minutes for questions. That's fine with you.
Okay. Yeah, but let me skip those two slides. They weren't so important anyway. Okay, so one thing that is maybe tangential to this talk, but is quite important, so I want to point that out, is that, of course, if you do few shots learning, then it very much depends on your choice of shots. So what we do here is we have different sets of 32 training examples. So these are these three sets, the three colors. So each set is randomly sampled from the training set and contains 32 training examples. And you see on these 5 tasks here that the average is actually quite different. So two of the sets get an average performance of 68, and one of the sets, set 2, gets a performance of 63. So that's quite 5% is quite a big difference. And I just want to point out that that is something I think that's under investigated. And I would also accept blame here as far as our work is concerned, because we didn't systematically investigate that, but we shouldn't have. We should have. So there's one recent paper also from our group on this problem, ACR 2021. So if you're interested in that, then you can check that out. So the choice of shots matters, and that's a source of variance that should be taken into account if you do experiments. Okay, let's turn to a comparison with GPT-3. So you're all familiar with GPT-3, I'm sure. So I'm just going to tell you what I find interesting about it. So it doesn't do supervised fine-tuning for a specific task. And that's very interesting, I think. I don't think it's technically so super interesting what they did at GPT-3, but the conceptual framing, I think, is quite interesting, because that's also the case for humans. We don't have silos for different tasks, arguably, but we can fluidly move between tasks and solve them. And we don't have a problem with a new task if it's similar enough to other tasks. And with supervised training, you always end up with these silos, with this discretization of tasks. And GPT-3 avoids that, so that's very nice. And so what they do is they have in-context learning. I showed you this example for machine translation earlier. So basically, the model just reads this prefix and then solves the task by predicting something. So so there are no parameter updates during this in-context learning. And you could argue that that means no real learning takes place for a specific task, because the parameters don't change. Of course, it uses the context to make a prediction, and in that sense, it's adaptable. But it's not true learning in the sense that no parameter updates happen. But arguably, humans do parameter updates when they learn. For example, you don't start from scratch when you open a second pomegranate a day later. You watch this YouTube video in the beginning of the talk. You retain some knowledge from that. And if you try to open a pomegranate tomorrow morning, you have that in your mind, and you can do a better job at opening a pomegranate. In contrast, GPT-3 arguably doesn't learn anything after the completion of pre-training. So if you metaphorically show the video to GPT-3 today, and then you give it a pomegranate tomorrow, it starts from scratch. It hasn't retained anything. So why not use both task description and supervised learning? That's what we do in PET. And that is what humans do, and I think that's the right approach. Another way of putting that is we don't want to tie our hands. We want to solve a task well, and therefore we should use all everything that's available to us to solve it well, all tools, and supervised training is certainly one of them. Just the history. So we published the first PET paper in January of last year, and GPT-3 came out in May May of last year. So I think our approach is definitely an interesting contribution to this debate. Of course, you could argue GPT-2 also already had some of these ideas, but it was not few-shot learning. And we do this combination of supervised learning and task description. And I think that's really key for actually realistic settings that occur in the real world. Okay, let's look at the size of the model. So GPT-3 has 175 billion parameters. We are also going to look at GPT-3 Med that has 350 million parameters. Then iPad has 223 million parameters, and that's the number of parameters of Albert XX large, which is the underlying model I'm going to use for these experiments that you will see on the next slide. So you have a huge model and a small model that has just 0.1% of the size of the large model. So we have David and Goliath here. David is iPad and Goliath is GPT-3. And here's a comparison of the performance. So let's just look at the average. This is on Superglue, 32 training examples. And so GPT-3 gets 73% on Superglue, and iPad 77. So you get a 4% improvement of iPad over the GPT-3 model. And I think that's quite a good result that such a tiny model, iPad can actually beat a huge model like GPT-3. And the reason, of course, is that we use supervised training. Supervised training is very powerful. So if you combine that with the idea of task descriptions, then you do better. And so I think it's a fair comparison. I mean, it's the same number of training examples. The same information is available to both models, but iPad makes better use of that information. So David won here in this contest. Okay, in the last part, I want to talk about debiasing, and this is quite different actually from the first part, but the same general idea is employed here, which is to use patterns and descriptions and instructions, in this case, I should say, for making use of the language understanding capabilities of this new generation of models. Okay, and so this is divided into parts, self-diagnosis and self-debiasing. Let's first look at self-diagnosis. Here's the basic idea of self-diagnosis. Upon self-reflection, people generally know whether something they said is considered biased. This is not true in all cases, so people may be less well informed about anti-transgender bias, so maybe they will say something that's anti-transgender and not be aware of the fact that it's anti-transgender. And of course, there's also the general problem that somebody may disagree with the assertion that something is biased. So they may say, I know that what I just said is considered biased by the liberal media or someone, but I have a right to say that, and I'm going to say it anyway. But even in that case, they are aware that the general judgment is that it's biased. So that's our assumption, that people in most cases know that something is biased when they say it. And our question is, do language models have a similar capability? Do they realize when they say something that is biased, that it's biased? And so in the experiment, the way we implement that is, this is the sentence that is potentially biased. And then we ask the question, does the above text contain Y? Where Y is some form of, this is now a little bit different, some form of toxicity. And the answer is then simply yes or no. So for example, I'm going to hunt you down is the sentence that we want to test. This is the question, does the above text contain a threat? So the category of toxicity here is threat. And then the language model answers either yes or no. And so if it knows that what was produced is biased, or is in this case toxic, then it will say yes, and otherwise it's going to be random. So for the experiments here, we use the 6 emotional concepts covered by the Perspective API. We use the real toxicity prompts dataset. From that, we take the top and bottom 10,000 examples for each attribute. So we have, for each attribute, we have a training set or a evaluation set of size 20,000 and 10,000 clear positive and 10,000 clear negative examples. And the self-diagnosis then simply consists of classifying the output, these 20,000 examples per toxicity category as biased or unbiased, which means the language model produces yes or no, and that's the answer, the classification decision we record. Here are the experimental results. So the baseline is 50%, since it's half-half, toxic, non-toxic, and the smaller models don't get above that baseline. So they basically don't know if something is toxic or not. They produce toxic stuff, but they don't know that they produced toxic stuff. But if we go to the very large models, then they do have an awareness of toxicity. So in particular, T5XXL has a accuracy of 0.87. So that's, I think, quite good. It's far from 100%, but we could imagine that something like that could be helpful in eliminating biased speech. Okay, and we can extend this idea to self-debiasing. And to do that, we create something we call an evil twin. And it's basically so we take a language model and then we create its evil twin, and it's basically the same language model, except it generates output that is conditioned to produce biased output. We're giving it a prefix that conditions it to produce biased output. And then we compute the difference between the prediction of the evil twin and the prediction of the original unchanged language model, and we discount the predictions by the difference. So I'm going to give you an example, and unfortunately it's going to be offensive, so I apologize for that, but otherwise it's not easy to explain. So this is our evil twin pattern. The following text contains y, x. So this is a form of bias, and then the language model is asked to generate something that is biased. So that's how we create the evil twin. So for example, it might look for gender bias, it would look like this. The following text contains gender bias : and now the language model is going to generate text. First the word women, then the word cannot, and then the word code. And this is presumably because we ask the language model to generate biased text. This is a made-up example, but I chose that for clarity. Okay, yeah, just a little bit more detail on, or maybe I'm going to skip that detail. I mean, basically, we simply take the original language model prediction and discount it by a factor if the evil twin gave a particular word. We do this word by word. So if the evil twin gives a particular word a high probability and the original language a low probability, then that's an indication that the word is biased, and then we discount it with a discount factor. So that's the simple implementation of this idea. And then the hope is that the discounted language model will produce something like women cannot be ordained, which is less offensive than women cannot code. Okay, here's the evaluation on Crow's pairs. And Crow's pairs consists of pairs of sentences. One is stereotypical, one is generic. And the idea is if the language model prefers the stereotypical sentence, then that means it has learned the stereotypes from its training corpus. And so the ideal result for language model would be 50%. That would mean that it randomly picks either the stereotypical sentence, the biased sentence, or the generic sentence. It gives both of them roughly the same probabilities, and that means it's not biased. So the higher it is above 50%, the more biased the language model is. And so we evaluate this here for our different bias categories in Crow's pairs. We evaluate BERT base, BERT large, and Roberta, and this is a comparison of the original language model and the self-debiased language model in each case. And you can see that we get a very nice improvement. Very nice debiasing, especially for Roberta. Roberta has a higher bias because it's trained on web data, and I think these results are quite nice. So it seems like self-debiasing is working, and it could be one quiver in one arrow in our quiver to fight against bias in NLP. Yeah, so LMs have a limited understanding of their own biases. We can exploit this for self-diagnosis and self-debiasing. This does not solve the problem of bias in NLP models, but it could be one tool in our toolbox. Okay, then I think I can stop at this point.
Okay, thank you very much. I think you introduced two very exciting topics. And now for questions. So I will continue with first calling people who did a question in the chat. So maybe Sabine, you have a very specific question.
Yeah, I was. Hello, Hinrich. I was interested in which was your best pattern, which was the worst pattern of slide 28. Do you remember?
I would have to look that up. I'm sorry. I knew it at some point, but I actually I don't think I will remember that. I can look at them again, but I think one of these two was the worst pattern, but I may be wrong. I would have to look it up. I apologize.
We found that pre-posing the targets, the artificial attention words, pre-posing it usually works better for our BERT models. That's why I was interested. But
what do you mean by so the
your review is sort of the standard input, right?
Yes.
And then your other thing is like, pay attention to this. That's really describing your task.
Yes.
And do that for relation extraction, where we have two entities given that we want to find the relation. And we do better if we pre-pose that to the text than post-pose it in the BERT.
So this should work better.
So that's in line with the two top ones, the two first ones being better than the two second ones. Yeah.
Okay. Yeah, I think that is also the case, but I would have to look it up.
Thanks. Sorry.
Thanks. Any other questions?
Yes, sorry, I had my mic muted. So I was saying, sorry about that. I was saying that if somebody wants to raise the hand, it's a bit hidden in this interface, at least in my case. You have to press the three dots and then there is the raise the hand icon. But I will continue with the questions in the chat. So next one is Ada1. Do you want to take the floor?
Ada, are you there?
Ada, are you there?
They said to go ahead in the chat.
Oh, which means
I can also read it if you hear me.
Okay, I can hear you now, yes.
Oh, okay, all right. So evaluation based on textual output has a long tradition in NLP. Are you convinced that it has ever been, or it is still a sufficient evaluation method? If not, how do you think we can move forward?
I'm not sure I understand the question. So let's say for sentiment analysis. So it's a classification task, and we want to know how well this model that we are proposing performs on the task of sentiment analysis. Are you saying that our model is inefficient, or are you saying that something in the evaluation could be improved? Or
I'm just not sure if what we are evaluating is actually orthogonal to how the model works, and how we're separating data from model. For example,
the data.
Are we actually just studying the idiosyncrasy of the data? How the patterns in the data, how the data is patterned, and how it's being formed and formulated?
I think it definitely depends on the pre-training corpus. So if we had a radically different pre-training corpus, then potentially the numbers would be very different. So the assumption is that the pre-training corpus is in some sense representative of, I guess, English. And maybe you're pointing to the recent literature that shows the problems with that approach, because we're using just a huge amount of data without really understanding what exactly is in that data. And I think that's certainly a problem. Yes.
Yes, that's also one problem. But I guess at the end of the day, I'm just not sure what we are really evaluating. I mean, given that language data is always going to be an instance of whatever this abstract language, a concept of language is, that we are always just going to be testing data sets. Yeah. An instance of this language, this concept language. So there will always be something in the data that will just be an instance of things so therefore we would always have something. We can always quibble about something. And are we quibbling about the data not being good enough, the model not being good enough, but at the end of the day, is there something that we can really use as the evaluation as to, for example, for sentiment analysis or for any NLP task? Is there ever a sufficient evaluation method that is not based on text that we can use instead of what we've been doing for the past decades?
I think the point of all this work on pre-trained language models is that we are using text. So I think it is certainly it's certainly true that it depends on the text, and that again, I would say the question is how representative is the text for English or for a certain type of English, and you can question that. We can have a debate about that. No, I completely agree with that. But I think it's I mean, we are not making, we are not using very complex or unusual phenomena here to do sentiment analysis. Sentiment analysis is a relatively simple task. And the type of information we need to extract out of the pre-training corpus, that our pre-trained language model needs to extract out of the pre-training corpus, is fairly simple. And so we are making the assumption that that's not a problem. You can question that assumption, certainly. But I think I personally don't see it as a problem. You have to make some assumptions when you do research, and that's an assumption we're making.
Okay, I'm just wondering if you, beyond this assumption, whether you have had any other thoughts on if this were not the right assumption, how else we could go about it.
No, I believe it's the right assumption, so I haven't really thought about.
Thanks.
Yeah.
Okay, thanks.
Okay, thank you. Chris, do you want to raise your question?
Yeah, sure. So we are on the right slide already. So to me, it looks like you have this prediction task, and you have the assumption that you can map every class to a single word, like here, terrible, bad, okay, good, great. So do you think that assumption always holds, or what would you do in cases where there would be also very good or things like that? Could you also deal with that?
Yes, I completely agree with your question. Of course, you cannot make that assumption in general. And this is in particular true if you have a large number of labels. So if you have just 5 labels, then usually you will get lucky, or you have a good chance of getting lucky. And you can find single words for these 5 labels. But you know, if you have 100 labels, then it becomes increasingly unlikely. And then you also usually have more complex categories that don't correspond to single words. So yes, that's a big limitation of what I've presented. But we do have a paper on using multiple verbalizer words or verbalizer expressions that consist of several tokens. It's not the most efficient way of doing it, and Timo is actually working on a different way of achieving the same result that is more efficient. But I think you're pointing here to one open area in this research direction.
Okay, thanks a lot.
Thank you, Matt Murphy.
My question was actually kind of answered by the examples, which made it clearer. So you can skip my question.
Yeah. Thank you, Thierry.
Oh, hi, thank you, Hinrich, for the nice talk. So you are using, for this to write, this type of class description as a pattern to inject human knowledge in the process. Did you also consider other type of pattern like definitions where humans typically express their knowledge about certain objects or events?
Yes, that's a very good question. And I think I mean, there are different ways to answer that that suggestion. One answer would be that the question is, how well can the language model make use of a definition? Because this here is very simple stuff, right? What you see here on the slide. A definition is more complicated, and we actually do have a publication that looks at trying to use definitions, and it seems like the language models are not doing that well at understanding them. So, for example, if you want to match definitions, so we've published a data set where we match definitions with contexts. And so you have to match the definition with the context. So you need to understand the definition, and you need to understand the context, and then you know whether definition and context are a match. And so language models are not very good at that. So I think using definitions would be a very plausible next step. But I'm not sure that our language models are up to that level that they actually can really understand the definitions. I'm not sure whether that answers your question.
It does. Thank you. Because we're trying to do something, and then maybe we should leave it.
You're trying to do the same?
Well, not with the definition, but summaries of tales, of folk tales, that give a kind of definition of this specific class of folktale, and try to see if we can match to for classifying real folktales. So,
and then you have it's not so easy to get it to work, or
we didn't start with it. It's a masterwork.
I see. Okay.
It was important for me to listen to your opinion on this.
No, I think it's very promising, and we didn't dig very deep into it. So far, maybe you have to, I don't know, reword the definition, or break it into parts, or yeah. So I think it is a very promising direction.
Thank you.
Okay, I think we have still time for 2 quick questions. Maria and then Desmond.
Can you hear me?
Yes, I can hear you.
Thank you. Thank you very much, Hinrich, for your great talk, and thank you, Enrico, for organizing this as well. So my question is, so I very much agree about exploiting human expertise for generating the patterns. I was more wondering on so how we ensure pattern diversity when we're sort of guiding for this, and I guess this to some extent depends on the task, and also if you found that actually the pattern diversity does matter. So a little bit more about kind of insights on this, I guess.
Yeah, great question. Thanks. So there's actually one detail I left out, because and it's the following. So the question is, if you don't have any feedback while you're writing patterns, then you're basically completely in the dark. So the question is, can you bring a little bit of light into the dark? And the way Timo does that is he uses the training set to test the pattern. So he uses the language model without fine-tuning it with the pattern, and sees how well it performs on the training set. For example, on the 10 examples in the training set. And often that's actually a pretty good indication whether the pattern is any good. And so if you know the first 5 patterns you try all don't get any of the examples right in that 10-shot training set, then maybe you should you know, look more widely for different patterns and keep going. So that's one element I would say in response to your question. And the other important thing is, and we're working on this right now, Timo is working on this right now, is that it seems like the variety is very important, but what's really important is you need to have obviously at least one good pattern in your set. And then actually it seems to be fairly robust against adding bad patterns. So if you have one good pattern and 5 bad patterns, it seems to be performing really well doing the ensemble, because I guess, yeah, we should actually find an explanation for that. But it seems to be very robust that way. So the problem is not adding lots of bad patterns. The problem is you need to find, obviously, at least one good pattern. I'm not sure I can give you a firm recipe for that. I think, yeah, the only indication you have in reality is what Timo is using, which is the zero-shot performance on the training set.
Thank you very much. Thanks. Thank you.
Hello?
Sorry, yeah, it's again me muting the mic. So Desmond, time for a quick question.
Hi, Hinrich. Thanks
Hi,
for the
Desmond.
talk. I really enjoyed this talk. It was great.
Thank you.
I had a question. I think the previous slide, you have a description of how you exploit, maybe it's a different slide, about how you can exploit multiple patterns in PET and you train n different models. Yeah, this one. So from this slide, it looks like you have a model, say Bert or Roberta, and you fine tune it on pattern 1. And then for pattern 2, you train Roberta again, but it's back to the original model. And so I'm wondering, why do you need different models here instead of kind of having multiple patterns with one backbone Roberta or Albert model?
Yeah, that's a good question. And actually, so Timo has published, I don't know how many papers on this, exploring different directions. And for example, he also has a paper on using this idea for sequence to sequence tasks, which I think is very interesting for summarization. And there he actually did exactly what you just proposed. So instead of fine-tuning the language model separately, he used a single language model. And I think the reason was that it's all much more expensive. And I mean, we are a university lab, so we don't have enough computers to do that for an expensive task like sequence to sequence. And so that's why he had to do it that way. I think the intuition here is that you get slightly better performance if you do the fine-tuning on each pattern, because if you're in a truly few-shot setting with just 10 training examples, you might get interference between the patterns. You could imagine, I'm not sure I can come up with a good intuitive example, but you could imagine that 2 patterns are kind of actually require opposite types of fine-tuning in different directions. Maybe because they use the semantics of the words differently or something like that. And then you could get interference that if you fine-tune them together in one model, then actually the performance is not going to be as good as if you fine-tune separate models for them. The disadvantage is, I think that's what you were alluding to, that it's kind of expensive. I mean, it's not expensive because it's very small training sets, so the computation is not that much. But of course, you have lots and lots of models, and that's kind of ugly. But I mean, storage space these days is cheap, so it's actually not really a problem.
Thank you very much.
Okay, thank you. Before saying goodbye to everyone, I just a small, I don't know if it's a question or observation, but does this sound like we are getting back to rule-based and knowledge engineers in a way? So we have annotators, for example, but we also now have people which is expert in writing these patterns. So is it in a way back to a few decades ago?
I think that in reality, people with expertise and putting their expertise into the whole machine learning ecosystem is always going to be very, very important, because we need inductive bias. Inductive bias has to come from somewhere. And I think so. Timo's motivation is he worked a long time as a consultant in industry where the consultancy goes to a big company and the big company has some problem, some NLP problem they want to solve, and so there's lots of expertise there. Somebody can explain the problem very well to you, but the amount of labeled data is very small, and either because of time constraints or money constraints or producing lots and lots of training data is not realistic. And so I think in that setting, that's the only game in town is really to use the expertise of the people who know the problem and can write patterns. They don't really want to, because they're very expensive, experts. They don't want to spend days labeling data, but to sit down and write patterns is something they can do. So I think, in my opinion, that should definitely be part of what we're doing. I wouldn't necessarily call it rule writing, but I agree, it's very similar. It's very similar to writing rules. Yes.
Mm-hmm. Okay. Thank you very much. Thank you to all the audience for the interesting questions, and thank you, Hinrich, for this exciting talk, and also staying up for all those minutes answering questions.
Yeah, thank you very much for inviting me, and thank you for these really great questions. I really enjoyed it.
It's been a pleasure. And just to remind everybody that there will be other seminars. By the way, this one was recorded and will be available in the URL that I just posted, together with the talks from last year and the upcoming ones. So thank you, everybody, and bye.
Thank you.
Thank you.
Yeah, thank you for organizing.